Good morning. Today we're going to discuss kinematics, motion along a straight line. First, let's have a review. What is kinematics? It is a sub-branch of physics which is under mechanics. Kinematics comes from a Greek word kinen, which means to move. It describes to us how objects are moving. Under this are the concepts of horizontal motion, which includes speed, velocity, and acceleration. It has also vertical motion and projectile motion. On the other hand, dynamics, as part of mechanics, is a study of the causes of motion and changes in motion. So it describes to us why objects are moving. Under this are the concepts of Newton's laws of motion, impulse and momentum, stability, and equilibrium. So before we move on in the discussion of kinematics, let's try to remember what is a frame of reference. During your junior high school, we already discussed this. A frame of reference is a point where movements are determined. Example, sumakay ka ng jeep. Nakita mo na umaandar ang jeep. Pinara mo ang jeep at ito'y huminto. Sumakay ka sa jeep at umandar na ulit ang jeep. Kung sumilip ka sa labas, nakita mo na ang gumagalaw ay ang mga tao at bagay sa labas ng jeep. Dahil dito, yung frame of reference ay ang loob ng jeep. Pero ang mga taong nasa labas, ang nakikita nila ay ang jeep ang gumagalaw. Ibig sabihin, ang kanilang frame of reference ay kung saan sila nakatayo. Nagbabago ang pananaw at nagbabago ang pagtakbo ng isang bagay o ang paggalaw ng isang bagay depende kung paano ito nakita. The Earth is the most common frame of reference. Bakit? Dahil dito tayo nakatira. Lahat ng bagay, lahat ng gumagalaw sa mundo, at lahat ng mga gumagalaw sa labas ng mundo ay laging relative sa pag-ikot at paggalaw ng ating daigdig. What is speed and velocity? What's the difference between the two? Speed is a scalar quantity. It's defined as the distance traveled by an object per unit time. The SI unit, the System International Unit of speed, is meter per second. The formula for speed is equal to the distance divided by the time. The equation for this is a small letter v is equal to d over t. Take note that the symbol for speed is small letter v and not s. On the other hand, velocity is a vector quantity. If you're going to remember, a vector quantity has both magnitude and direction. So we defined this as a speed in a given direction. It has two dimensions, the positive and the negative. When we have positive velocity, the motion should be upward or forward. For you to have a negative velocity, the motion should be downward or backward. The SI unit for velocity is the same as the speed. And the formula for this is velocity is equal to displacement over time. You will notice that we put an arrow on top of the symbol for velocity to signify that it is a vector quantity, same as with displacement. Acceleration. Acceleration is defined as the rate of change in velocity or change of velocity per unit time. Sabihin, pag nagbago ang velocity ng umaandar na sasakyan o umaandar na bagay, you have acceleration. It's either bumibilis o bumabagal. Formula for acceleration. Acceleration is equal to the change of velocity divided by the time. The equation A is the unit of acceleration, which is equal to the change, delta v, change in velocity divided by change in time. So that's delta t. Or the acceleration A is equal to the final velocity minus the initial velocity divided by the time. Let's now move on to the uniformly accelerated motion. The uniformly accelerated motion of a body moves on a constant acceleration. When an object moves with constant acceleration, the velocity increases or decreases at the same rate throughout the motion. The average acceleration equals the instantaneous acceleration when the acceleration is constant. A negative acceleration can indicate either of these two conditions. Number one, the object has decreasing velocity in the positive direction. Number two, the object has an increasing velocity in the negative direction. We have four usable and basic equations for uniformly accelerated motion. So the first equation is v, the final velocity, is equal to the initial velocity plus acceleration times the time. The second equation is that d, the displacement, is equal to 1/2 the initial velocity plus final velocity times time. The third equation is that d, the displacement, is equal to v sub 0 t plus 1/2 at squared. And the fourth equation is that v squared is equal to v sub 0 squared plus 2ad. Let's try to look into this table. We have here these four equations. And here are the given information, and here are the information given by these equations. The first equation gives us an information that the velocity as a function of time, which means that all variables are present except for the distance. So we can calculate for the given final velocity if we have the initial velocity, the acceleration, and time. The second equation gives us an information that the displacement varying with velocity and time. You will notice that acceleration is not present in this equation. The third equation, it gives us an information that the displacement as a function of time. You will notice that the final velocity is not included. So if you're going to solve for problems, we need to look into, in our fourth equation, we have this, that the given information is that the velocity as a function of displacement. So we can identify the velocity if we have a given displacement and a constant acceleration. Here, we don't have the time. Let's go into our first example. A boy is playing bihagan, or prisoner's base, agawang base. From rest, he runs to the other side with an acceleration of 0.02 meter per second squared to save his teammates for about 20 seconds. What is the distance between their base to the other side? Let's try to calculate. So here, we're going to answer our example number 1. So we have a given acceleration is equal to 0.02 meters per second squared. Time is equal to 20 seconds. Since the player or the boy comes from rest, the initial velocity is equal to 0. We are required to find the distance. Our equation that we're going to use is that d is equal to v sub 0 t plus 1 half a t squared. So for our solution, d is equal to v sub 0 t. Sorry, let's erase that. We need to be very careful on writing our symbols. V sub 0 t plus 1 half a t squared. So here we have to substitute. V sub 0 is equal to 0. So this, any number multiplied to 0 becomes 0. So we can cancel this out. So I have 1 half. Acceleration is 0. So acceleration is equal to 0.02 meters per second squared times 20 seconds squared. So d now is equal to 1 half 0.02 meter per second squared times 400 squared second squared. So we multiply this 0.02 meter per second squared and 400 seconds squared. So we can cancel this second squared. So we have now 1 half equal to 8 meters. So the remaining unit now is meter. So d now is equal to 4 meters. So this is now our final answer. So we have now example number 2. An airplane travels 280 meters down the runway before taking off. If it starts from rest, moves with constant acceleration, and becomes airborne in 8 seconds, how fast is the airplane when it takes off? Let's try to answer the second question. Let us answer now example number 2. We have a given of distance, which is equal to 280 meters, and an initial velocity of 0. And the time it takes for the airplane to take off is 8 seconds. We are required to find the final velocity. Our equation to be used is t is equal to 1 half v sub 0 plus v times t. Solution. We have t is equal to 1 half v sub 0 plus v times t. We multiply both sides first by 2, so we can remove the 1 half. Then we have now 2d is equal to v sub 0 plus v multiplied to t. So we need only d. So we divide both sides by t. So this cancels. So we have now 2d over t is equal to v sub 0 plus v. So to isolate the final velocity, we subtract both sides by v sub 0. V sub 0. So this cancels. So we have now v is equal to 2d over t minus v sub 0, where v sub 0 is equal to 0. So we have now v is equal to 2d over t, where it is equal to 2 times 280 meters divided by, divided by 8 seconds. So we have now v is equal to 560 meters divided by 8 seconds. So our final velocity is equal to 70 meters per second. So that's our examples for the uniformly accelerated motion. Let's move on now to our next discussion. A free fall is where an object moving under the influence of gravity only. It is a special case of constant acceleration that occurs for an object under the influence of gravity alone. If an object is thrown vertically upward or dropped, the acceleration due to gravity of negative 9.8 meters per second squared is substituted in the above equations that we have discussed a while ago. To find the relationship among the velocity, the distance, and the time. This definition of free fall leads us to two important characteristics about a free falling object. Number one, that free falling objects do not encounter air resistance. And number two, all free falling objects on Earth, as our frame of reference, accelerate downwards at a rate of 9.8 meters per second squared. A little rule to bear in our mind. All objects, regardless of their mass, experience the same acceleration when when it is in a state of free fall. When the only force acting is gravity, the acceleration is the same value for all objects. On Earth, this acceleration has a value of 9.8 meters per second squared, and it is given a special name of acceleration due to gravity and a special symbol of g. Let us take note that free falling objects are in a state of acceleration. The velocity of free falling object is changing by approximately 10 meters per second every second. If dropped from a position of rest, the object will be traveling approximately 10 meters per second at the end of the first second, then approximately 20 meters per second at the end of the second second, approximately 30 meters per second at the end of the 30 second, and so on and so forth. Let's look into this table. A while ago, I mentioned that a special symbol is given to the acceleration due to gravity. So we can change the acceleration A into the acceleration due to gravity, which is with the symbol of g. So here, we have v sub y, which is in the vertical axis, is equal to v sub y sub 0 plus gt, as an example for equation number 1. There are three cases of free fall motion. Number 1, objects drop, where the initial velocity is equal to 0. Number 2, the second case, objects thrown downward, where the initial velocity is not equal to 0. And the last case is that the objects thrown upward, where the final velocity or the velocity on the maximum height is equal to 0. The moment that we experience a final velocity at the maximum height at 0, we call it as a hang time. Let us watch this short video clip from TED Ed.
Michael Jordan once said, "I don't know whether I'll fly or not. I know that when I'm in the air, sometimes I feel like I don't ever have to come down." But thanks to Isaac Newton, we know that what goes up must eventually come down. In fact, the human limit on a flat surface for hang time, or the time from when your feet leave the ground to when they touch down again, is only about 1 second. And yes, that even includes his airness, whose infamous dunk from the free throw line has been calculated at 0.92 seconds. And of course, gravity is what's making it so hard to stay in the air longer. Earth's gravity pulls all nearby objects towards the planet's surface, accelerating them at 9.8 meters per second squared. As soon as you jump, gravity is already pulling you back down. Using what we know about gravity, we can derive a fairly simple equation that models hang time. This equation states that the height of a falling object above a surface is equal to the object's initial height from the surface plus its initial velocity multiplied by how many seconds it's been in the air, plus half of the gravitational acceleration multiplied by the square of the number of seconds spent in the air. Now we can use this equation to model MJ's free throw dunk. Say MJ starts, as one does, at 0 meters off the ground and jumps with an initial vertical velocity of 4.51 meters per second. Let's see what happens if we model this equation on a coordinate grid. Since the formula is quadratic, the relationship between height and time spent in the air has the shape of a parabola. So what does it tell us about MJ's dunk? Well, the parabola's vertex shows us his maximum height off the ground at 1.038 meters. And the x-intercepts tell us when he took off and when he landed, with the difference being the hang time. It looks like Earth's gravity makes it pretty hard for even MJ to get some solid hang time. But what if he were playing an away game somewhere else, somewhere far? Well, the gravitational acceleration on our nearest planetary neighbor, Venus, is 8.87 meters per second squared, pretty similar to Earth's. If Michael jumped here with the same force as he did back on Earth, he would be able to get more than a meter off the ground, giving him a hang time of a little over 1 second. The competition on Jupiter, with its gravitational pull of 24.92 meters per second squared, would be much less entertaining. Here, Michael wouldn't even get a half meter off the ground and would remain airborne a mere 0.41 seconds. But a game on the moon would be quite spectacular. MJ could take off from behind half court, jumping over 6 meters high, and his hang time of over 5.5 seconds would be long enough for anyone to believe he could fly.
So that's the hang time. So let's have now our next example. So a juggler tosses 3 balls alternately vertically upward. Each ball has an initial velocity of 5 meters. How high does each ball rise? How long does each ball remain in the air? So let's answer. So here we have the juggler that tosses the balls upward. So we have a given initial velocity of the balls, considering that they have the same weight and same structure with the same initial velocity of 5 meters per second. We are required to find the height and time it takes for the ball to be in the highest height. Our equation that we're going to use is the final velocity along y-axis is equal to the initial velocity plus, sorry, plus gt. And then the height is equal to vy sub 0 t plus 1/2 gt squared. So for our solution, need to get first t. So we use the equation vy is equal to vy sub 0 plus gt, so that we can use the time on the second equation that we have. So assuming that the ball's height is at maximum. Therefore, the final velocity is equal to 0. So we have vy is equal to vy sub 0 plus gt. So we can transpose and have vy minus vy sub 0 is equal to gt. Since the final velocity is equal to 0, we can remove this one. So we have now negative vy sub 0 is equal to gt. So to get or to isolate time, then we divide both sides by g. So we have now a working equation equal to negative vy sub 0 is equal divided by the acceleration due to gravity. So this is equal now to negative 5 meters per second. We have a positive value for the initial velocity because it is moving upward, divided by negative 9.8 meters per second squared. Let us take note that the acceleration due to gravity, whether an object is moving up or down, is still in negative. So time it takes for the ball is now equal to 0.51 seconds. So to solve for the height, we have now h is equal to 5 meters per second times 0.51 seconds plus 1/2 g 0.51 seconds squared. So the height now is equal to 2.55 meters, since this seconds here will cancel out. So that plus 1/2 9.8 meters per second squared times 0.26 seconds squared. So the seconds here will cancel. So we now have h is equal to 2.55 meters plus 1/2 2.55
We're right
meters.
here on the water.
So multiplying and adding this, we have multiplying this and adding this, we have the height, which is equal to 3.83 meters.
Again, the orange. Again, the orange. Look at
Thank you
this.
for listening. I hope you learned something.